Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to look at using Simpsons rule in MATLAB. And I'm going to start with a program in Young and Molenkamp's work that does the weights for the Simpsons rule. So if you'll recall Simpsons rule, you basically different terms get multiplied by the first and last by 1, and then you alternate 4, 2, 4, 2, 4 through your data set. And this technique only works if you have an even number of intervals or an odd number of data points. And so the way they propose setting this up is to create a vector of weights. So this is their code for this. So they start with a function, they're creating a vector w that is my simp weights of n. And so n is the number of terms that you want, or actually the number of intervals that you want. And w will be the column vector, and it will be of length n plus 1. First thing they do is they check and make sure that you actually do have an even number. And so they're looking for the remainder of n divided by 2. And if it is not equal to, so a squiggly line equals means not equal to 0. And so if the remainder is not 0, then you have an odd number. And so it will give you an error message saying that, yeah, you got to put in an even number. Once that's checked to make sure that you have an appropriate value there, then we're going to create a column vector. And they decided that the easiest way to do this was to create a column vector of all ones, or all twos, I guess. And so ones of n plus 1, 1 is this starting column vector, and then they say 2 times that, and they end up with a vector of length n plus 1 that is all a value 2. Then they set the first and last equal to 1, so w of 1 equals 1 and w of n plus 1 equals 1. And then every other, so 2 counting by 2's, so starting with the second, counting by 2's, until you get to n, they set every other entry equal to 4. Okay? So that creates the weight functions for the Simpsons rule. Then I've written this code for the my Simpson of x and y. So for a vector of x's with the corresponding y's, it will return a value of the integral. So first thing it's going to do is count the length of x, and then it's going to check and make sure that I have an even number of intervals, which means I need an odd number of data points. So if I count the length of x, that's my data points, I need it to be odd. So if the remainder is 0, it means I'm even, and so I've got a problem. So my check here is equals 0, so equal sign. Remember, for not equal, it's the squiggle equal sign. So first I check and make sure we have the right data set. Then I build the weighting function by using my simp weights of n minus 1. All right, the number of intervals, not the number of data points. Start my accumulator at 0. I'm going to let I go from 1 to n. So through my points, t equals t plus w of I times y of I. So this weighting times the value of the function. And then I'm going to take that, multiply by the delta x, and divide by 3, and that gets me an approximate integral. Now, before we were doing the function, the integral of from 0 to 1 of x cubed dx, and we know the answer is going to be 0.25. And the way we were doing it is we were setting up x equals 0 to 1, and let's count by 0.1. That's what we did last time. We could change it if you wish. And y is equal to, and we wanted x cubed, but I want it point by point cubed. I don't want to cube the vector because that makes sense. That's not even defined. And so there's my y and my Simpson of x and y. And I get this time 0.25. So it's getting the right answer. So that's all very reassuring. So that's the my Simpson. We actually can do f equals at x, at z. Let's do z, since I've already got x defined. Z, not to the 1/3, to the third. Don't need parentheses. Z cubed. And then I equals, there is a built-in function, integral of f from 0 to 1. And that does it also. And that's doing symbolic integration. So we actually have other options. We don't need to use the Simpsons rule or the trapezoid rule on something that can be symbolically integrated. But for definite integrals, we've got some choices, and we've now built our Simpson and our trapezoid rule functions. Thank you very much for your time.